Welcome back. In this video, we're going to apply some of the things we've learned into a textbook problem on fluctuating stress. This is an interesting problem because it has an unclear place where it might break. So the typical approach that we take when we're doing fatigue failure analysis is to evaluate whether or not we believe the particular location will fail. So recall, anytime we're talking about crack failures, cracks are real things that happen in real places. So we must be really clear and specify where it is that we're concerned about a crack growing. So in this particular instance, we have a odd-shaped bracket type thing, which has both a fillet and a hole. And so every time we see geometry change and we know that there's stress, like there's going to be stress concentration factors, but it's not super clear right now where that stress is going to be highest. So the only approach that we really have for evaluating this problem is figuring out the factor of safety for fatigue in both locations and comparing them and then going based on the lower one. So the two aspects of this problem that are a little bit different are, one, we have a fluctuating load, and number two is that we have two locations where we're concerned about the fatigue failure. Alright, so a lot of this is just applying the fundamentals, but we'll go ahead and make a nice solution process for ourselves to follow. The solution process that we're going to follow is first determine the material properties. Next, we'll need to determine the Marin factors to modify the endurance strength. We'll need to calculate stress concentration factors. We'll need to evaluate what are the mean and amplitude stress. And finally, we need to check for both yielding and fatigue failure. Alright, so that's going to be our solution process. So at the moment we don't know where it's going to break, either the fillet or the hole, so we're going to approach it from both locations. So you can read the description in this problem in the textbook, the 10th edition. This is Shigley's problem 630. Alright, first off we need to know the material property. Specifically the endurance strength, or the ultimate strength, the yield strength, and from that our hypothetical endurance strength. So our material was this 1018 steel, cold drawn, and we can look at the tables in the back of the book, and what you'll find is that the ultimate strength for 1018 cold drawn steel is 64 kpsi. In the ultimate strength, the yield strength is 54 kpsi, giving us a hypothetical endurance strength. Recall that's 50% of the ultimate strength at this range, which is 32 kpsi. All of these are in kpsi, thousands of pounds per square inch. All right, so our second job now is to modify using Marin factors. So our Marin factors that we'll consider are Ka, Kb, and Kc. Ka, the surface factor, we'll look at first. Recall that Ka takes the form of A times the ultimate strength raised to the B. And the only thing that we know about this part is that it is cold drawn. So from our tables, we can find those values for A and B. A is 2.7 and B is negative 0.265. Plugging in our values, Ka equals 2.7 multiplied times 64 kpsi raised to the negative 0.265, or Ka equals 0.897. We may come back here and change this to 0.9. All right, how about KB? KB is the size factor, and it depends on if you are in bending or torsion, adjusting the size of your piece. But we are not in bending or torsion, we're actually in axial loading. And by rule, KB, the size doesn't make any real difference when we talk about axial loading. Think for a moment why that might be. We'll do KC. KC is our loading factor, and this is axial loading, as I just said, which again by rule is 0.85. So all of these are the Marin factors we're going to consider, and together we can calculate our Marin factor, Ka times Kb times Kc times our hypothetical endurance strength. So altogether that is 0.9 basically times 1 for case B times 0.85 times our hypothetical endurance strength of 32 kpsi, giving us a modified endurance strength that we'll use in our Goodman equation of 24.4 kpsi. Let's see what our next step in our solution process was. We figured out material properties, we've modified our endurance strength with the Marin factors. Now we need to consider any stress concentration factors if there are any. Well, there are two locations where there are stress concentration factors, and those are the two locations we're concerned about failure. So specifically the hole and the fillet. So let's start with the fillet location. And we are looking at step 3 here, the stress concentration factors. All right, for a fillet of this particular loading, we need to find a graph and determine our KT from that graph. So let's go look for that. So first of all, we have the hole. That's one we'll want. We'll come back to that. But right now we're talking about a fillet. So an axial loaded flat plate type bar in tension. This is the situation that we're in. So we will look at the D over D and the R over D. So let's come back and figure out what those are. So R over D is equivalent in this situation. Let's go back to the figure for a moment. The radius here of that fillet was set at 1/4 of an inch. The small diameter is 3 inches, the large diameter is 3.5 inches. So let's put these together at the same time since we're looking at the figures all at the same time. So for the fillet, we had 0.25 inches divided by that smaller width of 3 inches. And the D over D line is 3.5 inches over 3 inches. So this is about 0.083, and this D over D is about 1.17. So for the hole, we'll have the size of our hole divided by the width of the part that remains. And based on that, we'll come up with our the line for our fillet. So that is 0.4 inches divided by the 3.5 inches, where that is. That's equivalent to 0.11. All right, so using those values, we can now come up with their theoretical stress concentration. That is KT. Since we are in normal stress, our KT is we're using KT as opposed to KTS. All right, so let's look at those figures. So for the hole, we can start off with, we have a D over W, and that value of D over W was 0.11, so we're pretty close to here. So at 0.11, very close to 0.1, and we can find our theoretical stress concentration is pretty close if we follow the 0.1 line up, we find it's pretty close to 2.7. So we'll use that as our theoretical stress concentration for the hole. KT equals 2.7. Now let's find it for the fillet. The D over D line that we'll be on was 1.1. A little bit higher than that because it was 1.17. And the R over D line on the vertical axis is 0.083. So we're close to a tenth there. So that looks like it puts us about KT of maybe 1.7. If 1.6 is halfway there between 1.4 and 1.8. So KT value of 1.7. Now notice the hole is much higher, but the stress value that we apply it to is going to be very different at the hole and at the fillet. So let's continue on. What is KF, our actual fatigue stress concentration factor? Well, it depends on our notch sensitivity, Q. So we need to find our notch sensitivity, Q. We do that by looking at the tables for the size of the notch and the stress concentration and the ultimate strength. So looking at table 620, or chart 620, we can see the notch sensitivity. We're working with an ultimate strength of 64 kpsi, which puts us on the lowest line. And we're looking at a notch for the fillet of about 0.25 inches. Which you'll notice puts us way off of this curve. So we can look at the end of the curve. Notice it kind of comes to an asymptote and maybe goes up just slightly as it's getting up there, because 0.25 is pretty good distance away. So we can make an assumption here. I wouldn't be, obviously it's going to be less than 1. It's pretty clear it's going to be less than 9. And it's going to be greater than 0.8. So based on those facts, let's call the notch sensitivity for that 0.85. We can do the same thing for the hole. We have the same, we'll be following the same line again, of course, but we have a different notch radius. This time, we'll use the radius of the hole. So remember the radius of the hole was the diameter was 0.4 inches. So this hole radius is 0.2. Again, we're well off of the curve. And since we're pretty close, this notch sensitivity would be fairly reasonable to also assume is 0.85. This allows us now to find our actual fatigue stress concentration factors. So KF for the fillet is 1 plus the notch sensitivity Q times KT, the theoretical, minus 1. Or in our situation for the fillet, we have 1 plus 0.85 times 1.7 minus 1. So KF for the fillet equals 1.295. Which is more digits than we need for right now, but we'll come back and clean that up later. We'll do the same process for the notch for the hole. This is KF for the hole. And doing that same process with the different KT value gets you a very similar stress concentration, but obviously a little bit higher, so 2.43. And again, these are just these are factors, so they do not have units. All right, so that finishes and completes step 3 for us of finding the stress concentration factors. Now we need to determine actual stress values. So let's go back up and look at our loading situation. As I said before, this is fluctuating loads. It's fluctuating between 5,000 pounds in tension and 16,000 pounds in compression. So more often than not, this part is being compressed. So at one, we'll draw out how that loading looks in just a moment. So for both the fillet and the hole, they experience different stress values, but they experience them in the same pattern. And that pattern looks like this. At some point, we get up to tension caused by that 5,000 pounds. And later, it gets to some very negative 16,000 pounds, the stress caused by that load. And then it fluctuates between there. So this is the situation where we're going to have a mean stress that is not equal to 0, meaning we are not fully reversed. This is that case 2 fluctuating load. So let's again look at it from the situation of both the fillet and the hole. All right, so what is the maximum stress that that part experiences? Well, this is just going to be F max, whatever the maximum load is, over the area that actually carries that load at the fillet. So in our situation, this is 5,000 pounds over the area, which is 3 inches, times the width of 1/2 inch. The maximum stress at that location then is about 3.3 kpsi, 1,000 inch-pounds. We can also figure out the minimum stress, which of course is just going to be F min over that area, since we're just talking about direct axial loading. So this was negative 16,000 pounds over that same area, 3 times 0.5 inches, or the minimum stress at the fillet location we calculate to be negative 10.67 kpsi. Let's go ahead now and do the same thing at the hole. So at the hole, we have a sigma max, again, due to axial stress, the maximum force at the area, but this time we're looking at the area which the load is carried over at the hole, which is basically the material that's left after you take the hole out. So that looks like, in our situation, 5,000 pounds divided by the width, which is the same, 1/2 inch, and this time we have the part, the 3.5 inches wide, except subtracting from that the size of the hole, which was the diameter of 0.4 inches. This gives us a maximum stress at the hole of 3.23 kpsi, fairly similar to what the maximum stress we'd see at the fillet. And we do the same thing for the minimum stress. We have negative 16,000 over 0.5 times 3.1. So a minimum stress of negative, this is compression stress, 10.32 kpsi. Great. So those are what the stress that we calculated, but recall we want to include our stress concentration factors. And we'll want to do that for both our mean and our amplitude stress. So let's go ahead and figure out what our mean and amplitude stresses are, including the stress concentration factors. So our mean stress is always calculated as the average, so that is the maximum plus the minimum over 2. We're going to go ahead and multiply that to include our stress concentration factor, Kf. So for our situation here at the fillet, the sigma mean, call it fillet, equals our maximum plus our minimum over 2. That is 3.3 plus negative 10.67 over 2. All of that multiplied times 2.295. Let's go ahead and just call it 2.3. So a mean fillet stress, mean stress at the fillet, is equal to negative, that is in compression, 4.75 kpsi. Our amplitude stress is calculated in a similar way. So our amplitude stress for the fillet, to be clear, is the absolute value of the maximum minus the minimum over 2. And again, we'll multiply times our stress concentration factor. So you can do that math fairly straightforward. So the fillet, the amplitude stress is 18.13 kpsi. We can do the same process for the whole. The only thing that changes is everything. Our maximum stress and minimum stress values are different. Our Kf values are different. But we'll get the same sort of process. The mean for the whole is equal to negative 8.62 kpsi. And the amplitude for the whole is 16.5 kpsi. All right, so now we're at the place where we can actually decide whether our part is going to break or not. So first of all, let's check for failure in yield and then for fatigue. So we'll check for yielding failure first. So our yielding stress, we'll use von Mises approach, is the yielding stress compared to the von Mises stress. So what's the maximum value for that von Mises stress? Well, recall if we just have one stress value, it ends up being that stress value squared and then the square root of that. So a negative or a compressive load becomes just evaluated as the same thing as the von Mises stress, right? So if we square value and then take the square root of it, we end up losing that square in there. So for the most conservative estimate, we'll put in the highest magnitude stress, which in our situation happens to be the minimum value of stress that we see in this situation, or the most negative value of stress. Our yielding strength for the fillet is the 54 kpsi. This is, our yielding factor of safety is the endurance strength, or the yield strength, 54 kpsi, divided by the magnitude of the compressive stress. So that is, if we take that von Mises stress, we'd have 10.67 kpsi, which says our yielding factor of safety is 5. So more than likely, it will not break. This means it will not yield. But that doesn't tell us, are we going to get an infinite number of cycles out of this thing? To do that, we need to use our fatigue fatigue factors of safety, which we can use the Goodman equation, which looks like sigma A over SE plus sigma M over the ultimate strength. And we have all these for our fillet. So 1 over NF for the fillet is equal to our values from before, which was 18.13 divided by the endurance strength, (24.4) plus the mean stress, which had a value of negative 4.75, over the ultimate strength of 64 kpsi. Now notice that on average this part tends to be in compression. That is, the mean stress is negative or less than 0. And if that's the case, then the way this is formulated would actually benefit us and say that we could get more cycles than we'd likely actually be able to get out of it. So anytime our mean stress is less than 0, we basically discount it from our Goodman equation, and we'll only be looking at the actual stress, the amplitude stress. Again, that's because compression tends to not allow cracks to grow. It tends to keep cracks together. So our fatigue factor of safety, just including the fillet, just including the amplitude stress at the fillet, ends up being 1.356. All right. So it's either that or the hole. So we'll do the same process now for the hole. We can check for yielding at the hole using the same process, except now we have 54 kpsi divided by 10.32. Again, we can take that most minimum, square it, take the square root out of it. We basically get rid of that. And our yielding factor of safety is about the same, 5.32. So it also is not going to yield. Our fatigue factor of safety, also, we have a mean stress, which is less than 0. And so we will ignore its contribution to the Goodman equation and just look at the amplitude over the endurance strength. So our NF in this situation equals 24.4 endurance strength over our 16.5 amplitude stress. This ends up being NF for the whole of 1.48, which is slightly higher than it is for the fillet. So the answer to this question is the fatigue factor of safety for this part is NF equals 1.3, maybe 6. We can round up a little bit, and it will break at the fillet. And that basically wraps up this problem. And what we've done is we've looked at a fluctuating load in uncertain locations where we had to look at least 2 locations. If you have a much more complicated part, you may have to look at more locations. But for this situation, the 2 was enough. We figured out the material properties. We modified the endurance strength, hypothetical endurance strength with the Marin factors. We determined stress concentration factors at both the fillet and the hole, applied those stress concentrations to our mean and amplitude stresses, and then applied both the yielding failure criterions as well as the Goodman fatigue failure criterions, and identified which is more likely to break. From our analysis, we would say that it's more likely to break at the fillet, but we have at least infinite life. Well, that'll about do it for this video. Until next time.